And I'm recording. Okay. So, part B, what's this flux through one of the 6 faces of the cube? Well, that's, I mean, the whole scenario is pretty symmetric. So, if that was the flux through the whole thing, just divide it by 6. That's the flux through one of the surfaces. So, divide by 6 is 179. All right. Does everybody like that one? I can tell Cassie liked it. She was pretty happy. There was no vectors involved or anything. So that was a level 1 problem. Here's a level 2. We have charged paint spread over a very thin uniform layer of a plastic sphere, diameter of 10 centimeters, giving it a charge of minus 10 microcoulombs. Find the electric field just inside the paint layer. So we didn't actually, this was the one thing, Gauss law, we didn't make it to last time, but it's pretty simple, so let's talk about it just real quick. We're actually going to do this in lab today. One thing that, so in a conductor, the electrons are free to move anywhere they want to, right? So they're all going to move out to the surface because while they're repelling each other, they want to be as far away as they can. So the best thing they can do is all get to the surface. One thing that comes from Gauss, so let's have an imaginary thing. I mean, if it's solid, then okay, all the electrons are on the surface, and even if it's hollow, though, all the electrons are still going to go to, you're going to wind up having they're still only going to go to the outside surface. The only way you would actually get anything on the inside surface, which you can do this with Gauss law, it's not that hard, but if you actually had some sort of a charge, either positive or negative here in the middle, then that could make it on. But if it's just kind of sitting out there by its own in the real world, everything's always on the most outside surface possible. So charge on surface. Another thing that comes from that, the electric field on the inside is always 0. Because, well, if there was an electric field, it would move the charges around, but the charges are free to move, so basically they're going to move around until the field becomes 0. I mean, in real life, it's not quite 0, but it's pretty damn close. Okay. Outside, this is the only one I would want to do. Basically, you do it the same way you do the parallel plate capacitor one. Since I know the electric field is 0 on the inside, on the outside, it's basically like half of that parallel plate capacitor drawing. So you wind up getting just barely outside. E is sigma over epsilon naught. Whoa, and it stopped working. And it's restarting. Okay. So outside, you get that E is sigma over, let's do it again. It's sigma over 2 epsilon naught, which I will.
It's 2 epsilon naught?
Yeah, it's 2 epsilon naught. So for a parallel plate capacitor, it's just epsilon naught because the 2 plates are both adding to it. Okay.
I'm with you.
Let's. See if I can get OneNote to come back up. Yes. Okay. Okay, you can do it. 2 epsilon naught. And it's perpendicular. So the normal vector just says, oh, the direction is perpendicular to the surface. Okay. Cool. So let's go back to the problem. What's the electric field just inside the paint layer? So, well, this isn't a conductor because it's plastic, but it's hollow. So it's kind of the same principle applies. So inside the sphere, the electric field 0. Don't even have to think about it. Right? Was that? You like those, don't you? Just outside the paint layer. Well, we can actually do this one of two ways. Let's use what we just learned though. So if the charge over the whole thing is minus 10 times 10 to the minus 6, right? That's the charge on the whole sphere. To use this formula, though, I need to know sigma, remember, is the surface charge density, which means charge over surface area. Right? So the surface area of a sphere, I need to divide this by 4 pi r squared, which r was 10 centimeters, right? Yeah. So 4 pi times 0.1 squared. Come on, move. There we go. All right. Excuse me. So 10 divided by pi divided by 4 divided by move some more. Oops. No. Divided by 0.1 squared is that. So that's everything except the 10 to the minus 6 is what I plugged in. So the sigma is negative 7.95 times 10 to the minus 6 coulombs per square meter. And then, so just take that divided by 2 epsilon naught. So then I need to divide by 2, 8.85 times 10 to the minus 12. So divided by 8.85, divided by 2, and I've got to 10 to the negative 6, or no, 10 to the positive 6. So it'd be 4.50 times 10 to the 5th. If I did my mental math right. Come on. What is that? I don't know what that is. 4 point. I forgot it. Oh, crap. Okay. Yeah, 4.5. Oh. No, I messed something up. What did I mess up? Let me do this the other way just real fast, just to double check. If I did it the other way, it would be 10 divided by... Well, it is 10 to the 6, but it's 0.4, which would mean it's 4 point times 10 to the 5. Let me stare for a second. So the other thing we could do would be to go 4 pi.
I'm going to bet on calculator.
That's quite likely. The other thing is the thing I thought was 2 might not actually be 2.
Well, it would make sense because it would divide it by half.
Yeah. Let me do the Gauss law computation in my head real quick. So the flux is just going to be sigma times A, or sorry, it's just going to be A times E. On the other hand, it's actually, no, I don't think it has a 2. Let me double it and see if that works. Let me change it to None.
How come it's positive? Instead of negative 5, it's positive 5.
It is positive 5 because it's the top was 10 to the minus 6, the bottom was 10 to the minus 12.
Gotcha.
So the 12 becomes
Yeah,
positive.
positive.
Actually, since you said that, though, that makes me think, wait, is the electric field positive or negative? Because you know how I am with those things. No.
Sometimes this thing, it'll tell you to check your sign, and then sometimes it won't.
Yeah, that's a good point. It probably would have told me check my sign. Okay, so let me do this the other way real quick. So the other way it would be 10 divided by, or let's just say times 9 divided by r squared, so 0.1. Oh, that is 9 times 10 to the 6th. I'm going to feel really stupid if that's all that was wrong with it. Because Colby told me to check that. I thought I was right. Nope. All right. So I'm just going to give up. That's nothing. What? No, it's not.
I'm really wishing I had my calculator right now.
What did I do wrong? Let's go ahead and do part C and then come back and think about it. So for part C, basically when you get outside the sphere, it's just going to be like it was a point charge, which is how I tried to do part B the second time, because it should be the same thing. So this should be 9 times 10 to the 9th, and then 10 microcoulombs. And then 10 centimeters, which we're going another 8.5, so 18.5 centimeters. Which this is all just 10 to the 4th if you stack all those together. So 9 divided by that thing squared. My calculator got closed apparently. I don't think it does either. Of course, I can't say that's completely unusual. So 262 and then times 10 to the 4th would be 2.63 times 10 to the 6th. Let's try that. So, okay, apparently I'm just doing something wrong. So I'm going to cheat. Oh, holy hell. Because I can't read. So the 10 centimeters isn't the radius, it's the diameter. So change all the 10s to 5s and we would be fine. Oh my word.
Did you find out through all that your signal was wrong?
What?
The exponential on your signal should be -10, not -6.
It actually should be.
Right. Because, well, I don't know, I got
Hey.
like 3 times.
Yeah, that's what I got, but then
What do you do?
whenever I did it the second way, I got 10 to the negative fifth, or 10 to the sixth. So anyway, so divide that by, okay, so this is, okay, why is it deleting everything as soon as I write?
So we can either just put point one or take the
So-
number out, right?
Okay, so like on part C, change the 0.1 to 0.05 and then plus 0.085 squared. And then same thing for part B, you just go, okay, 9 times 10 to the 9, 10 times 10 to the minus 6. And instead of 0.1 squared on bottom, go 0.05 squared. That does solve the
3.18 to
answer to that one was 3.6, and this one I didn't actually do. Let's see. So I got that, but that's wrong. So times 0.185. Whoops. And divide that by 0.135. So let's change that to 494. See if that works. Okay, yeah.
I'm still trying to get the first answer right.
That one. So that one should just be 9 and then divided by 0.05 squared.
Where'd you get the 9 from?
So the K is 9 times 10 to the 9th.
Gotcha.
So 3.6 times 10 to the 7th. Yep. So again, as far as the difference between doing this and doing this, apparently it doesn't have a 2 because, yeah. They're really the same thing because if I put a 4 pi here, and 4 pi there, what's that equal to right there? Q divided by 4 pi r squared. That's charge over area of a sphere. So this would be the same thing as if I went 4 pi k times sigma. But what did we learn about? So we did this last time. We saw that k was really the same thing as 1 over 4 pi epsilon naught, right? So this is just sigma over epsilon naught. So apparently there's not a 2 in there, even though it feels like there should be. But on a side note, maybe there's a 2 in the parallel plate capacitor just up top instead of down bottom. But no, that wouldn't work either. Yeah, I think it's just sigma over epsilon naught. It really feels like there should be 2.
So
but
the
there's
answer
not.
is, okay, I
Yeah.
finally got it there.
Okay, you finally got it.
3.59.
All right, that should not have been nearly as hard as it was.
Take